Okay, so I know this is not an ideal situation this way, but it is really cold outside, so I am not going to stand outside to do a video lecture. And since I have nothing on rotational kinetic energy in terms of problem solving, this was my second best option. So until I can get back outside, I thought at least you could have one to look at the process. So your problem reads, imagine a small helicopter has 3 blades. Each blade is 3.7 meters long and has a mass of 70 kilograms. So the length is 3.7 meters and the mass is, I've already forgotten, 70 kilograms. All right, so imagine the helicopter blade looks like that. So it's spinning, this is a top-down view. Okay, we're gonna model these as thin, solid rods with the axis of rotation right through that end, perpendicular to this plane, so sticking out towards you. If the blades are rotating at 400 rotations per minute, what is the kinetic energy, rotational, of this system? All right, so we know that our kinetic energy relationship is 1/2 the moment of inertia times omega squared. So we need both the moment of inertia for these 3-blade propeller and omega in radians per second. So let's start with that. We have a rotational rate of 400 rotations per minute. We know that in one rotation we have 2 pi radians in one rotation. And we, of course, know that there are 60 seconds in 1 minute. So if I determine my rotational, my angular velocity in radians per second, I get 41.9 radians per second for my omega. All right, so that's going to go into that relationship. Now, the next thing we need to determine is the moment of inertia. Well, if we're modeling these rotor blades as thin spherical rods rotating about the end, the relationship for the moment of inertia, and these are standard relationships you can look up, is 1/3 the mass times the length squared. Now I have 3 of them, okay, so we're gonna have to keep that in mind, but we'll find the moment of inertia for a single blade, the kinetic energy of a single blade, and then since we have 3, we can multiply that by 3. So we have 1/3, the mass is 70, and our length is 3.7. I'm going to square that. And we find that our rotational inertia for a single blade is 319.4 kilograms times meters squared. So if I use both of these relationships in my kinetic energy, and we have the kinetic energy is 1/2 times 319.4 times 41.9 quantity squared. I'll just grab my calculator. All right, and this we find equals 2.8 times 10 to the 5th joules. Now that is the rotation of kinetic energy of a single blade, but this system has 3, and so it has 3 times the kinetic energy. When I multiply that value, 3 times the kinetic energy of one blade, we get a total kinetic energy of 8.4 times 10 to the 5th joules. So that's the kinetic energy, rotational kinetic energy of the entire rotor on that helicopter.